Good day. Today we are going to discuss about the examples of configurations. I have here three examples of configuration, but first let's tackle about Reye configuration. Reye configuration was introduced by Theodore Reye in 1882. It is a configuration of 12 points and 16 lines. Each point of the configuration belongs to 4 lines, and each line contains 3 points. Therefore, in the notation of configurations, the Reye configuration is written as 1 2 4 1 6 3. The Reye configuration can also be realized by points and lines in the Euclidean plane by drawing the three-dimensional configuration in three-point perspective. An 83-1-2-2 configuration of 8 points in the real project plane and 12 lines connecting them with the connection pattern of a cube can be extended to form the Reye configuration if and only if the 8 points are perspectively projection of a parallelepiped. That's according to Servatrus and Servatius 2010. According to Aravind 2000, pointed out that the Reye configuration underlies some of the proofs of the Bell-Quotient-Spiegel theorem about the non-existence of hidden variables in quantum mechanics. Also, the Pappus configuration may be formed from two triangles that are perspective figures to each other in three different ways, analogous to the interpretation of the Reye configuration involving desmic tetrahedra. If the Reye configuration is formed from a cube in three-dimensional space, then there are 12 planes containing 4 lines each, the 6 face planes of the cube, and the 6 planes through pairs of opposite edges of the cube. Intersecting these 12 planes and 16 lines with another plane in general position produces a 163-24 configuration, the dual of the Reye configuration. The original Reye configuration and its dual together form a 284-284 configuration according to Grunbaum and Rigby 1990. There are 574 distinct configurations of type 124163 according to Bethen and Bethen 2005. Our second sample is the Cremona-Richmond configuration. The Cremona-Richmond configuration is a configuration of 15 lines and points, having 3 points on each line and 3 lines through each point, and containing no triangles. It was studied by Cremona by 1877 and Richmond 1900s. It is realized quadrangle with parameters 2, 2. Its Levi graph is the tooth-Cosetter graph. The points of the Cremona-Richmond configuration may be identified with the 15 ways of partitioning the same 6 elements into 3 pairs. These partitions are called synthemes. Identified in this way, a point of the configuration is incident to a line of the configuration if and only if the duad corresponding to the point is one of the 3 pairs in the syntheme corresponding to the line. The symmetric group of all permutations of the 6 elements underlying this system of duads and synthemes acts as a symmetry group of the Cremona-Richmond configuration and gives the automorphism group of the configuration. Every flag of the configuration can be taken to every other flag by a symmetry in this group. The Cremona-Richmond configuration is self-dual. It means that it is possible to exchange points for lines while preserving all the incidences of the configuration. This duality gives the tooth-Coxeter graph additional symmetries beyond those of the Cremona-Richmond configuration, which swap the two sides of its bipartition. This symmetry corresponds to the outer automorphism of the symmetric group on 6 elements. The Cremona-Richmond configuration also has one parameter family of realizations in the plane with order 5 cyclic symmetry. According to Ludwig Scalfi, in 1858 and 1863, he found cubic surfaces containing sets of 15 real lines and 15 tangent planes, with 3 lines in each plane and 3 planes through each line. Intersecting these lines and planes by another plane results in a 153-153 configuration. The specific incidence pattern of Scalfi's line and planes was later published by Luigi Cremona in 1868. The observation that the resulting configuration contains no triangle was made by Martinetti by 1886, and the same configuration also appears in the work of Herbert William Richmond by 1900s. Visconti in 1916 found the description of the configuration as a self-inscribed polygon, and according to H. F. Baker, used the four-dimensional realization of this configuration as the frontispiece of 2 volumes of his 1922 to 1925 textbook, Principles of Geometry. Zacharias of 1951 also discovered the same configuration and found the realization of it with order 5 cyclic symmetry. The name of the configuration comes from the studies of it by Cremona and Richmond. Perhaps due to some mistakes in his works, the contemporaneous contribution of Martinetti fell into obscurity. The third example is the Desargues configuration. Desargues configuration is a configuration of 10 points and 10 lines, with 3 points per line and 3 lines per point. It was named after Gerard Desargues and closely related to Desargues' theorem, which proved the existence of configurations. So there are different dimensions. The first dimension is what we call the 2 dimensions. In 2 dimensions, 2 triangles ABC, caps lock, and lower ABC are said to be in perspective centrally if the lines AA, BB, and CC meet in a common point called the center of perspectivity. They are in perspective actually if the intersection points of the corresponding triangle sides x is equals to AB intersecting AB, y is equals to AC intersecting AC, and z is equals to BC intersecting BC, all lie on a common line, the axis of perspectivity. Desargues' theorem in geometry states that these two conditions are equivalent. If two triangles are in a perspective centrally, then they must also be in perspective axially. The vice versa. When this happens, the 10 points and 10 lines of the two perspectives together form a instance of the Desargues configuration. On the third dimension, although it may be embodied in 2 dimensions, this Argus configuration has a very simple construction in 3 dimensions. For any configuration of 5 planes in general position in Euclidean space, the 10 points where 3 planes meet and 10 lines formed by the intersection of the 2 planes together form an instance of the configurations according to Barnes 2012. This construction is closely related to the property that every project plane that can be embedded into a three-dimensional projective space obeys this Argus theorem. This three-dimensional realization of the Desargues configuration is also called the complete pentahedron according to Barnes 2012. While the 4 dimensions, the 5 cell of pentateuch have 5 vertices, 10 edges, 10 triangular ridges, and 5 tetrahedral facets. The edges and ridges touch each other in the same pattern as the Desargues configuration. Extend each of the edges of the 5 cell to the line that contains its offline hull. Similarly, extend each triangle of the 5 cell to the 2-dimensional plane that consists it. and intersect this line and planes by a three-dimensional hyperplane that neither contains nor is parallel to any of them. Each intersects the hyperplane in a point, and each plane intersects the hyperplane in a line. These 10 points and lines form an instance of the Desargues configuration according to Barnes 2012. Although this Argus theorem chooses different roles for its 10 lines and points, the Desargues configuration itself is more symmetric. Any of the 10 points can be chosen to be the center of the perspectivity, and that choice determines which 6 points will be the vertices of triangles and which line will be the axis of perspectivity. The Desargues configuration has a symmetry group S5 of order 120. That is, there are 120 different ways of permuting the points and the lines of the configuration in a way that preserve its point-line incidence, according to Stropel 2013. The three-dimensional construction of the Desargues configuration makes these symmetries more readily apparent. If the configuration is generated from 5 planes in general position in 3 dimensions, then each of the 120 different permutations of these 5 planes corresponds to a symmetry of the configurations according to Barnes 2012. The Desargues configuration is self-dual, meaning it is possible to find a correspondence from points to one Desargues configurations to lines of a second configuration, and from lines of the first configuration to points of a second configuration in such way that all of the configuration's incidences are preserved, which was also according to Cossiter 1964. So those are the 3 examples of configuration. Hope you learned something. Bye!